All right, let's get into it. Today we're cracking open a true legend, i.e. Irodov's Problems in General Physics. Now, if you've ever studied physics, you know this book and its reputation for some seriously tough problems. We're going to jump right in and tackle problem 139, and we'll break this thing down together step by step. Okay, so what are we dealing with here? We've got a point moving along a circular path of radius r. Now, here's the twist. Its velocity isn't constant. It actually depends on the distance it's traveled, s, according to the formula v equals a times the square root of s. Our job is to find the angle, which they call alpha, between the total acceleration and the velocity. This is a fantastic problem because it really makes you think about what acceleration truly is. So let's lay out the game plan. We've got our givens, a circular path, radius r, pretty simple, and we have this specific velocity function, v equals a root s. This means the farther the particle goes, the faster it gets. And our goal, to find, is that angle alpha between the total acceleration and the velocity, all as a function of the distance s. Now, before we just dive into the math, let's take a step back and think about the physics. Whenever something moves on a curved path, its acceleration is basically multitasking. It's got two distinct jobs to do. Any idea what they are?
And here they are, the two faces of acceleration. First, on the left, you've got tangential acceleration. You can think of this as the gas pedal or the brake. Its one and only job is to change the object's speed. Then you've got normal acceleration, which you've probably heard called centripetal acceleration. This is the steering wheel. Its job is to change the object's direction, constantly pulling it toward the center to keep it on that circular path.
So the total acceleration that the particle feels is literally just the vector sum of these two components. And that right there, that's our whole strategy. It's a classic divide and conquer approach. We're going to figure out the tangential part, then the normal part, and once we have those two, finding the angle between them is going to be the easy part.
All right, let's do it. First up, step 1. We need to find that tangential acceleration, the component that's responsible for making our particles speed up.
So what is tangential acceleration, really? Well, by definition, it's just the rate of change of speed over time. In the language of calculus, that's simply dv by dt. It tells you how fast your speed is changing at any moment.
And we've hit our first little puzzle. The formula needs dv dt, the change with respect to time, but the problem gave us velocity as a function of distance, s. So how are we supposed to connect those two? What do we do now?
This is where a super handy tool from calculus comes in to save the day, the chain rule. It's the perfect little trick for this exact kind of situation. It allows us to relate the derivative with respect to time to the derivative with respect to distance.
Okay, let's break this down. The first part of our chain rule is dv over ds. So we take our velocity function and differentiate it with respect to s. That gives us a divided by 2 times the square root of s. Easy enough. Now for the second part, ds over dt. Wait a second. The rate of change of distance with respect to time? That's just the definition of velocity, v. And we know v is a times the square root of s. So now we just multiply those two pieces together. And check this out. This is the really cool part. The square root of s on the bottom cancels out perfectly with the square root of s on top. The s variable just disappears. This means our tangential acceleration is actually a constant. It's just a squared over 2. It doesn't change at all as the particle moves. That's a very clean, very neat result. Okay, one component down, one to go. We're halfway there. Now let's switch gears and calculate the normal acceleration. Remember, this is the component that's doing all the turning. Now this one's probably a bit more familiar if you've done any circular motion problems. The formula for normal or centripetal acceleration is just v squared divided by the radius r. This calculation should be a lot more direct. And yeah, this one's much more straightforward. We just take the standard formula, v squared over r, and plug in our expression for v. So we square a times the square root of s, which gives us a squared times s, and we just put that over r. Done. So our normal acceleration is a squared times s over r. And notice the big difference here. Unlike the tangential part, this one does depend on s. It gets bigger as the particle travels farther. Excellent. We've got both pieces of our acceleration puzzle. We have the tangential component and the normal component. We're on the home stretch now. It's time for the grand finale, putting them together to find our angle, alpha. So let's just visualize this for a second. The velocity vector is always pointing forward, tangent to the circular path. Our tangential acceleration, w sub t, points right along with it. The normal acceleration, w sub n, points straight toward the center of the circle at a perfect 90-degree angle to the velocity. So you see what that creates? These vectors form a beautiful little right-angled triangle. And the angle we want, alpha, is between the total acceleration, our hypotenuse, and the velocity. Okay, time to dust off that high school trigonometry. We have a right triangle. We know the length of the side opposite to our angle, that's wn, and we know the side adjacent to it, that's wt. So, what's the magic function that connects the opposite and adjacent sides?
SOHCAHTOA, right? It's got to be tangent. The tangent of our angle alpha is simply the length of the opposite side over the length of the adjacent side. In our case, that's just wn divided by wt.
Now, all we have to do is plug in the values we worked so hard to find. On the top, for our opposite side wn, we have a square s over r. And on the bottom, for our adjacent side wt, we have that constantly found, a square over 2. And here's the best part, where the math just cleans itself up. Look at that. The a squared terms on the top and bottom, they just cancel out. All of that work simplifies down to this wonderfully simple expression. The tangent of alpha is just 2s divided by r. That's our answer.
But hey, we're not just here to crunch numbers, right? We're physicists. Getting the formula is great, but what does it actually mean? What's the story this little equation is telling us about the particle's motion? This is the really key takeaway. Think about it. Right at the beginning, when the distance s is 0, tan alpha is also 0. That means the angle is 0. The total acceleration is pointed purely forward, right along with the velocity. It's all gas pedal, no steering wheel. But as the particle moves and s gets bigger, the value of 2s over r also gets bigger, which means the angle alpha gets larger. This tells us that the normal, or turning, part of the acceleration is becoming more and more dominant compared to the tangential speeding up part, which we know is just a constant.
And as a quick check of the book confirms, we nailed it. You gotta love when a complex-sounding problem boils down to such a clean, elegant relationship. That's what makes physics so satisfying. So, what Irodov challenge should we tackle next? Drop a problem number in the comments below. Thanks for joining me on this one.